All right, so a few years ago, College Board decided we didn't have enough to do in our curriculum, so they added the objectives of integration using long division and integration using completing the square. So in this video, we're going to focus on integrating indefinite and definite integrals using both the method of long division and completing the square. So far, up to this point, we've learned different techniques for integration. We've certainly done our fair share of integrating using U substitution. We've integrated the exponential functions. We've also looked at integrals of trigonometric inverse trig integrals. All right, we've looked at going back to an ln function when integrating. So what happens when all those techniques of integration fail us, but yet we have an integration problem that we have to find an antiderivative for? Well, that's what this video is going to show us, is two more techniques for integration. So let's look at the definite integral from x equals 0 to x equals 3 of this rational function. Oh, let's not forget the dx. All right, so this problem appears and we've got to begin to think about that integrand and how am I going to integrate that? Should I use U substitution? Well, if I attempted to use U substitution, I'd have to let U be the numerator because I have a higher degree here than I do here. Problem is, I don't want to let U be the numerator if I'm going to go back to an ln answer. So it looks like U substitution's out. All right, well, what else can we do? Can we cancel anything? Can we bring up the denominator? Yeah, we could bring up the denominator, but that would be quantity x plus 3 to the negative 1 that I can't do anything with as far as multiplying it inside to the numerator. So we're stuck. This problem is designed for us to use long division. So when you kind of get stuck with integration, and if your numerator's degree is higher than your denominator's degree, 2 is bigger than 1, you might want to think about coming over here and performing what we call long division. And you might remember long division as far as the words long division, but let's review how we're going to take this rational function and long divide. So the denominator is what we call the dividend. Okay, and then, it's the divisor. The numerator is the dividend. Now, if we're missing any terms, as we go from the high exponent of 2 down to the constant, we have to fill in spacers of zeros. All right, so what we did when we did long division is I would have my students cover up everything but the first term in the divisor and the first term in the dividend and ask myself, what do you multiply x by to get x squared? Well, we need to multiply by an x, and it doesn't matter where you place this x. Our next move was we back multiplied, we distributed x into x plus 3. So when you multiply, you get x squared. It must line up with another x squared term. When we multiply, we get 3x. And we line it up with the other linear term. Then we subtracted, which subtraction means we got to change the sign of everything that's here. Then we added down. These will cancel. That was the intent. If these two terms don't cancel, then that's a built-in red flag. Add these down, and we're going to get x plus 5. Then we start the whole algorithm over again. Cover up everything but the first term in the divisor. And this line, what do you multiply x by to get x? Then you go back and multiply 1 into the x plus 3. And then don't forget to subtract. These will cancel. And I'm left with the remainder of 2. Well, how do we represent that remainder of 2? Well, I come back up here and go, I have plus 2 remainders, and we can put it over the divisor x plus 3. So when you're trying to integrate this and your degree of your numerator is higher than this one, you might want to think about long division. So let's come back into the problem. So when I long divide, I'm going to take the quotient and the remainder, and that's going to be my new integrand. So notice that we have 3 terms, 1, 2, 3. This antiderivative is easy, this antiderivative is easy, and this one is actually going to go back to an ln answer. So the first thing I'm going to do is with without breaking this apart into 3 different integrals, I'm going to think this antiderivative is x squared over 2 plus x plus, now if I want this integral right here, I might pull the 2 out front and leave the 1 over x plus 3 inside the integrand. Okay, I know it's going to take me a little more time to work on this one, but don't forget the definite or the limits of integration. So I'm going to bring down x squared plus or over 2 plus x plus, now right here, if you did a u substitution, u would be your denominator. du becomes dx. So I end up with 2 times the definite integral from x equals 0 to x equals 3. Where dx is, I can substitute in du, and I still have the 1 over u. Hopefully you've committed this integral formula to memory. So x squared over 2 plus x plus, this is going to be 2 ln absolute value of u. This goes back to ln. Let's pull in the u. Let's go ahead and pull in x plus 3. But I'm going to do a big bracket here and put my limits of integration, 0 to 3. So the work I have left is to substitute in 3 for all the x's and 0 for all the x's. So that's the next work. So 3 squared is 9/2 plus 3 plus 2 times ln of 3 plus 3 is 6 minus. Now I'm ready to plug in 0. And don't forget to do a parenthesis here because you're going to subtract maybe a bunch of terms. But how nice is that that's 0, plug 0 in here. So all I'm subtracting is 2 ln of 3. Okay, this year the AP exam is all strictly free response, no multiple choice. You don't need to do anything further with this. If this was a multiple choice question, this answer likely would not be there, and I think it's worth at least doing this problem one time as far as a cleanup. And what I mean is this: we're going to go back to Algebra 2 and log properties. So let me go ahead and combine this fraction here. So 3 is really 6/2. So I'd get 15/2 from the constants. Now right here, I don't need these parentheses anymore because I don't have multiple terms. So what I'm going to do is I'm going to take the 2 from both these terms and factor it out. So not done, haven't gotten to the log properties yet. 15/2 plus, what I'm going to have here is I'm going to be using the quotient to difference property, or actually the difference back to the quotient. So I'm going to stack the 6 on top and the 3 on bottom. This is a log property. And then I would cancel that or divide this out to a 2. So my final answer would be 15/2 plus 2 ln of 2. Okay, this problem appeared on a multiple choice exam, and that was the answer that we were expected to get to. Again, this year's exam is going to be free response, so don't waste your time simplifying anything. Just abandon and walk away. All right, so let's do another long division problem. All right, spend some time looking at the integrand, making sure that you're not going to be doing a lot of work for nothing like the long division. Is there another way I can integrate that? Okay, for this particular problem, no. Pause the video, try the long division on your own, come back and check to see where you're at. I have a remainder of 1, so it's plus 1 over x plus 1. Oh, this upper limit's 2. Otherwise, I would be done, and that answer would have been 0. So I'm going to pull over the quotient and the remainder. I'm going to go through and find the antiderivative of all three of these terms. So this first term goes to x squared over 2. 5 goes back to 5x. And this is an easy integration, and that's just going to go back to natural log of your denominator. I'm going to do a big bracket, and I'm going to put the limits of integration 1 and 2. So plugging in 2 here, 2 squared is 4, that's 2. 2 here is 10. That's natural log of 3. Minus, I'm going to do a parenthesis because when you subtract, you're going to have to distribute that negative through all the terms. That's 1/2. That's 5. Plug in 1 here. ln of 2. Again, if this is a free response this year, just leave it. Otherwise, you just do a cleanup on it. You distribute the negative in and then clean up the constants and the ln piece of this, which that probably would be another log property like we had up here. You'd have ln of 3 minus ln of 2, which is ln of 3/2. But for where we're at this year, let's just leave it like this. Okay. All right, try u substitution. That's always the first thing I try. Well, u would have to be the numerator, and I can't have that if I'm going to go back to ln. So one of the things you can think about, well, the degree of the numerator is larger than the degree of the denominator. So, I mean, you might want to think about long division. Okay. And we're actually going to try long division and see what happens. I hope some of you guys see a different strategy. Okay. Because that's where we're going to get to. Let's just say that you tried to do long division on this one. Let's see what happens. Notice that you go from a cube to a linear term, so you're going to have to fill in a 0x squared. You may or may not need it, but we have to fill it in. I multiply x squared times x to get x cubed. I multiply that back and I get x cubed. I subtract. And then I have a 0x squared, which that kind of goes away. I don't even need it. And I have a 2x plus 1. Because this degree is higher than this degree, I can't do any more divisions. So I end up with the remainder, which is multiple terms, over the divisor. So let's just think about how we would integrate. This term's easy to integrate. How would we integrate this term? Well, try u substitution. If u is x squared, then du is 2x, but we need a plus 1, and we can't bring in an add-in or a subtrahend, they call it. We can't bring in addition or subtraction, so we just did all that long division work for nothing. But that should tell us we're missing something. Okay, what's another technique of integration here? And I'm hoping some of you guys said, I'd bring up x squared and make it x to the negative 2 and multiply it in. Perfect. What's the alternative to doing that? Break apart, share the love. So from the very beginning, I wouldn't even have tried to do long division, because when you divide by a monomial, one term, my first go-to thought is, let me break this apart. So what's x cubed divided by x squared? Then I think about what's 2x over x squared. The x's divide out, and I'm left with 2 over x. And 1 over x squared. Now to get ready for integration, I'm going to go to this middle term, and I'm going to pull up x and make it 2x to the negative 1. And then here, to get ready for integration, x to the negative 2. Now all terms can be integrated. I've got 2. Let's just focus on what is that antiderivative. And if you remembered, it's ln of absolute value of x. Good job. This antiderivative is not ln because this exponent's not negative 1. This is the reverse power rule. So I'm going to add 1 to the exponent, and I'm going to divide by negative 1 the new exponent. Well, that's going to change this plus sign to a minus. This is an indefinite integral. We don't have limits of integration, So we can't plug any numbers in. So this is when we add our constant of integration. All right, and I believe I have one more long division example. So you guys write down the problem and then pause the video, try it on your own, and then come back and see where you're at. Long division actually works on this one, but I'm not going to waste the time. I'm dividing by a monomial. I'm going to break this apart. Let's integrate and then evaluate at the limits. No plus c. Evaluated e. When you plug in e is already a positive number, so the absolute value bars are rendered useless. Minus, do a parenthesis. This year's AP exam, abandon, walk away. If it's multiple choice, which is where this appeared, okay, you'd want to go in and say, hey, that's 1. ln of 1 is 0. Let's clean it up. So e squared over 2 minus 1 minus a half. Common denominator results in 3 halves. So hopefully with those 4 examples, you feel somewhat comfortable with the technique of integration using long division. Time to move to what happens when we can't do long division and our other techniques of integration are not helpful. All right, we have 3 examples with completing the squares. Okay. If that problem appears, then in order for us to integrate this, try and tackle u substitution. If use the denominator, you don't have an x on top, so that's out. Does it look like one of those inverse trig integrals? Not really. There's no square root that would suggest that this would go back to arcsine. For arctan, there's not a square root in the denominator of arctan, but we only have 2 squares for arctan. So what we've done so far isn't helpful until a few moments from now. This is actually an arctan integral, but we have to make it look like an arctan integral, where the denominator is u squared plus a squared. So we're going to complete the square. All right, and again, long division doesn't work because the degree of the numerator is not bigger than the degree of the denominator. So let's just focus our attention on some work that we're going to do with this denominator. Let's complete the square. Let's write down the first 2 terms. Let's leave a blank, and then let's put the plus 13 here. Okay, way back in Algebra 2, when we wanted to complete the square, we looked at the b value. Remember, a is 1, b is 6, and c is 13. We took half of b and we squared it. So half of 6 is 3. We square it. I'm going to add a 9 here. But I don't want to change the value of this denominator, so if I'm going to add a 9 here, I've got to come over here and subtract a 9. If you cancel these 2 9s here, you're back to what you had, and that's where we want to be. We want to have equality. All right, so the next thing is we focus our attention on these 3 terms. This is going to factor into the binomial square x plus 3. If I factored, I would get back to quantity x plus 3. This constant comes from half b, and we pull the square on the outside. Clean this up, and we get plus 4. We just completed the square on the denominator of this integrand. So let me write it as the completed square form. And don't forget your dx. Okay, so now we might identify this as an arctan integral. Let's come over here and identify what a is. Well, a is what I can square to get this constant. A is a constant. So I'm going to let a be 2. I'm going to let u be the quantity x plus 3. And I'm going to differentiate u. So that's du equals dx. So what I see here is when you complete the square, I'm going to take the denominator and I see x plus 3. I'm going to make that u squared. Where I see 4, I'm going to take a, which is 2. The square root of this is 2. And I'm going to say this is 2 squared, or a squared. Where I see dx, I'm going to substitute in du. I think the way you learned the arctan integral was maybe, I'm going to come over here, something like this. You might have seen it as 1 over a squared plus u squared du. But it doesn't matter the order here. All right, for this format right here, which is equal to this right here, the antiderivative was a constant multiplier, 1 over a. So you've got all your ingredients right here, 1/2. We went to arctan, and we built a fraction, and we put u over a. We have an indefinite integral, so we put a plus c. So for completing the square, we end up with an arctan integral. Okay, we're supposed to integrate. Notice that sometimes they stack the dx on top and sometimes they lay it out to the side. It doesn't matter. You could put the dx over here and put a 1 up here. So how do I integrate this? Well, u substitution's out. Okay, it will be an arctan, but I've got to complete the square on the denominator. Leave a blank, put the plus 7 here, and then you need another blank. Half of b squared. If you put a plus 4 here, I got to put a minus 4 here. Clean these two numbers up, factor this into a binomial square. Return to the problem. I'm going to do a little work on this first. I'm going to look at 3 and what's its format of a square. It looks like this. If I square rooted 3, I'd get square root of 3. And then don't forget your dx. All right, so what's a? Square root of 3. U. This derivative is just dx. U squared plus a squared du. That's the arctan integral. So 1 over a, arctan, u over a. Indefinite integral, so we need a constant of integration. And no, you don't have to rationalize, we're wasting time. Been there, done that. One last problem. And we need a dx, and sometimes it's right here. Well, again, u substitution won't work because I don't have a 2x on top. That 2 is kind of bothering me. I'm going to move it out front. I notice that I'm going to have to complete the square, so I'll come over here and do that work. Half of b is 1, square it is 1, and subtract a 1. I'm going to pull the 2 up front, leave the 1 here. I'll go ahead and rewrite the 4 as 2 squared, get that out of the way. And then I've got my dx. Goes back to arctan. So don't forget your 2 up front times 1 over a, 1 over 2. Those will divide to a 1 later. And the final answer is just arctan of this argument, x plus 1 over 2. All right. So the 2 new added techniques of integration, long division and completing the square.